Hello, this is GDC Day 2. This is going to be the last of the summit talks. So the talks from here on out are going to be much smaller. Give me a second to drink this. Same idea again, we're going to start with this introduction. So we're going to break down all the math talks, because that's the talks I went to today. The math talks. I'm going to talk about some miscellaneous stuff that happened at the end, such as the social stuff, and then I'll summarize. I'm going to keep my explanation is shorter this time, mainly because I don't think I need to explain all the details. I'm just going to focus on more higher level stuff, except for quaternions, because I actually think I want to explain that a little more detail, because I can. But because I got a lot to cover, and I want to save on file space, and the time it takes to upload these, I'm going to challenge myself to keep these brief. So, I got late to this talk, the first one, which is height maps. It's about the usage of height maps. And what a height map is basically, it's a texture or a file or an array of floats which saves the heat of something. Like, for example, how many times the player has walked around. It could add a tick to a cell every time you move into the cell. So it starts increasing, this map of where the player has been. That would be a height map. It's all about these, it's like a contour map, if you think of geography, where it's like those rings of elevation. That would be a height map. You're trying to measure that's what it's getting the name from. What it's doing here in the talk was about all the different kinds of height maps and all the different applications of height maps. And there's a lot, I can't explain all of them, but there's the cool ones. Basically, you can use height maps in many situations where you need to figure out quick paths. Like you can store, for example, the closest path to a given point, like an exit. And so then map all the cells, each store through a Dijkstra algorithm, the closest, the distance that you would take to get to the goal. But there's other kinds of maps too. If you want to measure opacity, you could have an opacity map, which tells you visibility. Knowledge maps, your awareness of something. Oh God, well, that's the radiator. Forgive me for the annoying noise. But there's knowledge maps which deal with awareness. How basically fog of war, where are things going to be? A lot of this is about playing around with the A-star algorithm, which you can play around, which is a pathfinding algorithm. And these maps are really useful for speeding up A-star calculations. In fact, there's an entire section, because A-star is about like creating a list and storing states to a list. You could actually make 3 maps which handle all those states instead, which is a really interesting one, and it makes it go even faster. There's even more. There's also influence maps, which are for like how much influence an object has, like lighting or gas or anything with propagation. Anything with something is spreading out is what influence is great for. Because it's the opposite of a distance map. It's how far, instead of figuring out the point to a goal, it's how far are you from counting. Instead of counting up to a point, it's counting down. So the further something away, the closer it is to 0. And then it will check out. Great for light, like Minecraft light, for example. But the main idea here is that height maps are great for efficiency because you can store all these different kinds of calculations and then look them up from this array and use them in your calculations without having to recalculate them every single time. Great for terrain maps, collecting data, even for randomizing and making meandering routes by adding noise to A-star. That's another thing you can do. They mention also some optimizations involving byte maps. I won't worry about that too much. That's the main idea. Height maps are really cool. I found this was a really good, concise talk. I wasn't there for all of it, but I only missed like the first 5-10 minutes. I got most of the talk, unlike the water one. So this one I think is quite good, concise, clear. I understood what the use cases for everything. Really interesting. If you could somehow get GDC Vault or see this in a few years, check it out. It's good. There's one about mobile math. So this is like math that you would have in mobile games. Stuff like how do you handle dragging, creating a joystick, wheels. When you click and make a wheel, dragging things. That's what this is the math for. And it turns out a lot of the stuff, I feel like if you've done any math in 3D space, a lot of this math should come up and be familiar to you. We're talking stuff like projecting or transforming out from projection space into world space to get for object picking and stuff like that. This should come up. Anything to do with mobile, or if you work in Unity for like UI, this will come up too. If you're trying to use an UI element and have it interact with the real world or world space. The result is that while some of this is interesting, I guess to me, because some of these problems I've never encountered myself, I already knew most of this math, which felt good in the sense that I knew most of the math, but I didn't learn as much from this. I was surprised here and there, but this was mostly a lot of things that I was somewhat aware of. The main thing I learned about what you should use for stuff like tilt controls, which is to use the accelerometer. You don't use the gyroscope. The gyroscope has a whole bunch of problems. You want to use an accelerometer, or at least that was the presenter's opinion, which was a bit counterintuitive. But besides that, this was okay. There were some interesting things, some interesting nuggets. Not really for me. Not my thing. But I feel like if you want a refresher on this kind of math, check it out once it is released in 2 years. Quaternions. So, okay, the 2 talks I sat through were both about quaternions, but one was first about explaining quaternions, and the second was about generalizing quaternions, which means applying them to more than just rotation and translation. And because this was so, I think, very good at explaining what quaternions were, I want to try to do it myself. So the visuals did help. If this is one of those waiting for 2 years, if you find this on YouTube, check it out. It's called like a visual guide through quaternions. Go check this out. This is a good one. But here's the takeaway. Here's my summary. So quaternions, how they work is that you're encoding in the first 3, x, y, z, a rotation around 180 degrees. That's all it's doing, no matter what the number is. If the number is, say, 2, you get like 0, like the 2, like 0, 2, 0, 0. That's just still 180 degrees. It's like a normal vector. Even if your normal vector is 1, 0, 0, or 2, 0, 0, or 0.300, it's all the same direction. We do not care about the number, we care about the number. It's all equivalent. This is why we normalize it, because it makes it easier for us to handle the fact that it's just direction. It standardizes it for us. We don't get these equivalent magnitudes that then starts to mess with the math. And we can normalize quaternions, and we do that. We normalize quaternions for a similar reason, since we're encoding rotation. The W should be thought of as a identity value, or how similar it is to the original rotation. Like if I have this pencil, if I had, say, the Y value was 1 and the W was 0, we have no similarity. I rotate 180 degrees straight away. But if I want like a 90-degree rotation, then we want the W to be something we add to the W value, and then we normalize the quaternion. So it would become 0.7 something something, and then 0.7 something something for the W. In fact, this is how you can calculate the points. Like if you imagine the unit circle, then the similarity to the line, which would be your 1xyz, would be one value, like your x, and then your similarity to the original rotation would be your y, like your down if it was a unit circle. That makes it a bit more confusing. Just remember, everything is always versions of 180 degree rotations, and then you use a W to control how close you want it to be to that 180 degree rotation to reduce it. If you take two quaternions that are of different axes, add them together, then you get a new rotation around a new axis, like 1, 1, 0, 0 would be 180 degrees around the 1, 1, 0 axis. So that's all you need to remember. That's like the main idea behind quaternions. I think it helps you understand them visually so much better once you have this idea. For reference, I actually even wrote out for each of the unit rotations what it would look like. Like a 0001 is a rotation 360 degrees around It's just, that's what it means. Because it's basically saying that it's a, actually I think I got that wrong. I think it's -1. Yeah, because 0001 is a 0 degree rotation. You got full identity. It's exactly the same as the rotation that you started with. A -1, a 000 -1, means you're going 360. It's the complete opposite rotation. But it looks the same, so it doesn't really do anything when you do that. But that's kind of the idea. I hope this helps get a better picture of it. From there, we get into stuff like how you convert from axis angle to quaternion, quaternion division, what it means. There's dual quaternions, which is encoding a rotation and a translation. This is like quaternions, it has a lot more, it's a little faster and it requires less adds and multiplications than a traditional 4x4 matrix. So it's a little more efficient. There are still use cases for matrices over quaternions, as the guy himself mentioned. I asked him about it and he pointed out, like vertices, you would still want to use a 4x4 matrix. But in transformations, you would ideally want to learn quaternions because it would be more efficient. And it's great for things like interpolations, linear, smooth interpolations, all that jazz. So this is the entry-level stuff. You're following me so far? We just discussed it. It's all about 180 degree rotations around various axes that get combined, and with the W value we control the similarity to the original rotation, to the first rotation, to your first orientation, I should say. That's our main idea. From there, you can apply that same logic to any geometrical problem, or any 3D geometrical problem that you could handle in like 3D space, like a line plane intersection test, or projecting a point onto a plane. Like all the stuff you would use linear algebra for, you could actually just use quaternions for. And this is what the second talk was about. It was about explaining how this would work and what you do. And it's basically using reflections to accomplish these transformations. By using these reflections. And he's basically arguing that you could describe all of the processes as just different kinds of reflections. And you can describe things like planes, for example. A normal vector, for example, is a point that's infinitely far away It's just a distance to a point infinitely far away from the plane. That's a normal vector. Or the sphere, the skybox sphere in your world is a normal vector. Is a plane, and it's infinitely far away. That's like, these are some of the ideas that come up. I know it sounds a bit weird, but that's just sort of how it rolls. But using these quaternions and using flectors, which are reflection vectors, you can solve a bunch of these different problems by using the geometry and math associated with quaternions. And by generalizing it, you can basically help make your math more efficient and more simpler, because it's handling all these other cases without having to make edge cases in your code. So that was the Quaternion talks. Really interesting. I found them fascinating. The generalization bit, I think I would need to do some reading or refreshing and remind myself on terms, and my notes aren't the best in the world. But I would love to see this talk again in a few years, because I think it's such a great reference. I can't wait for it to come out. Practical projective geometric algebra. This is like the final boss of the math talks. I'm going to talk about it, frankly, like unlike the mobile one. This is the exact opposite of the mobile one, where I actually have a hard time understanding bits of it because it's going a bit over my head. I understand certain concepts because I've heard of them before when I've done math. Like, for example, there's more than one different kind of norm. Like when you do your x squared plus y squared plus z squared square rooted, your length calculation for a vector. That's called a square norm, or a Euclidean norm. But there's a whole bunch of different kinds of norms. You can actually generalize what a normalization. And that comes up here. That's an important concept here. So stuff like that I'm aware of. But then it starts going into wacky places, like there are anti-scale, like for example, there's this whole concept where every operation has an inverse operation. And there's this operation called wedge, so there's an anti-wedge, so there's anti-wedge products, and there's also not just scalars, but anti-scalars and anti-vectors, and my brain collapses. The thing is, the takeaway here is that while there are some specific use cases where this math would actually be better and is useful, and the guy has used it, there's also other bits of math that are frankly just not useful at all. Like transformations using projective geometric algebra are too expensive, or actually less efficient than just doing it the normal way. I imagine you might, if you were really clever, you might combine it with quaternions or something, or if you knew what you were doing. But the result is that while there are use cases like you can have really fast inversions, it's a bit more niche. But that is the talks. I know I want to use more fast this time, not as in depth as I blow by blow as the last one. But I think I got a better idea about what I want to communicate more here. And a lot of this I don't think I could really explain well. Sum up the other things of the day, I met with my friend Sam, and we hung out and got lunch. And that was nice. It was nice to see him again. I haven't seen him in a while since I graduated. So it was nice seeing and hearing from him again. So we talked about life and such. So I got to catch up with him. Hopefully I'll catch up with him some other time during the week. Moving on from that, I went to Exola game night. Basically, they had a bunch of snacks and a bunch of Mattel games, and you played those. And I played Uno with some Square Enix, a European Square Enix support team, an indie guy at Blowbox, something Box. Box was in the name. He didn't have a business card, unfortunately. So I have his information on my phone, but I'm using it for recording, so I can't check. That's unfortunate. Here are the business cards I got. This is Sam's. I think it's a cool one. If you solve the puzzle, that's right here, you can get his Steam key for his game. So that's a cool one. I actually really like his card. I think it's very neat. This one was done by a guy who's almost graduating from game art, his game art program, and I think it's very good pixel art. I think it's a very cute card. This was a card from a guy I met at the Exola event. And he showed up later because, see, after we played Uno and the Square Enix guys and the indie guy left, a new guy showed up. I think it was Jake. And he had this game called The Way. I don't think actually his name is Jake. But this guy showed up and he had this game called The Way, and he asked us to play it. He asked if we would like to play it. And I was intrigued, so I and the other guy were intrigued, so we kept playing it. And basically it's a card game. It's like a deck builder. It has the kind of verbs you would see in a deck builder, but you have one shared deck, so you don't build a deck. And the idea is you want to get exactly 8 points, and each of the cards you play have positive and negative points. And you have cards that can rotate other cards and destroy cards, and those apply to both you and the other player. So your goal is to try to control the board so that they don't get positive 8, and that you get positive 8. It's still being tweaked. I thought it was a very fun game, though it can be a bit swingy because some of the cards can be, when turned over, can jump you up in points in a large way, and you just win when that happens. So certain combos can end the game in ways you can't predict and you can't really counter. But when it's going, when it's not too swingy, it's quite fun. I can't wait for him to flesh it out more and do more testing. The art was very pretty. What he basically did was he used photography to take pictures of his hands, and he had all these nice gestures. But he also had like props too, like his hand would hold something, like an orange. And then he would take an image, and then he would then blend the two together through something like an AI program. For an example of this technique, this actually is used by Ebsynth. It's not necessarily AI, as far as I'm aware, but Ebsynth is doing something similar. It's the program that Joel Haver uses for his animations, for reference. Basically, it takes an image, he takes a keyframe, he draws over the keyframe, and then using the keyframe, it figures out how to draw over the rest of the images in the shot, and then basically rotoscopes the rest of the shot. Same kind of idea. His thought was, if he was going to release it, he would actually try to commission an artist for it. But as placeholder, it's a good placeholder. It sells the fantasy very well. It was a fun game. I'm curious to see how that turns out. Overall, a good day. I learned a lot, covered a lot of ground. Tomorrow is going to be more of the actual expo and the talks. I mean, not the talks, the booths. So I'm going to be doing more of those, less of the talks. I'm going to be having to talk more about the booths, and I'm going to have to figure out to get more aggressive with networking and attend things like the speed networking events. I might just do one a day of the speed networking events, because I like those from virtual, and I think it would be really fun. I found a really good time with them last year, so I think I should find some slots, mark them down, get there, get in, get out. If that happens, I'll also take notes as well. But yeah, productive. I hope I can get some more networking done tomorrow. I had a good time, got some nice food. I might go to a party tomorrow. We'll see how I'm feeling. Today was already pretty exhausting. But we'll see how I feel. Anyway, goodbye and good night.